doesn't have to be the case, right? So suppose otherwise. Otherwise, f is not constant. All right, so apply the extreme value theorem. That one. All right. Then there exists, let's say, C and D in the closed interval from A to B, for which f of C is greater than or equal to f of x, and f of D is less than or equal to f of x for all x in AB. Right? Since it's continuous, it has to reach a minimum and has to reach a maximum value. Right? Since f is not constant, there exists x naught in AB such that f of x naught is not equal to f of a. All right? So then you have two cases, right? Either f of x naught is less than f of a, or f of x naught is greater than f of a. All right? We can agree with that, I think. So if f of x naught is greater than f of a, then f of a is not the absolute maximum, and therefore we deduce what? I think I forgot to say something here. We're going to suppose, well, no. Okay, never mind. I'm about to add something. Didn't need to be added. I mean, this shows you that f of a is not absolute minimum, right? This would show you that f of a is not the absolute maximum, right? So in particular, that means f of a is what? Not equal to so that would tell us that C, let's see here, which was the absolute minimum? This one, right? So this would say that D is not equal to A, right? And this one would say that C is not equal to A. Let me just take a step back here and try to complete the thought here. So why does that matter? Right, so the thing is here, we know that the absolute maximum and absolute minimum, right? They have to be in the closed interval A to B. And what we're arguing right now is that since it's non-constant, there has to be at least this point x naught, which is not equal to f of a, right? And that means either, either D is not equal to A, D being the absolute minimum, or C is not equal to A, being the absolute maximum, right? So in either one of those possible cases, there is either an absolute minimum or an absolute maximum for this function, which is happening inside the closed interval. That means that f of D local min, in this case, f of C local min. Right? They're not the endpoints. But then by Fermat's theorem, what's that tell us? Fermat's theorem says that f prime of D is equal to 0 in this case, and f prime of C is equal to 0 in that case. But that exhausts the cases, because either it's less than or greater than f of x naught. In all possible cases, we see that there exists a point in the open interval, right? So here D is an element of AB, and C is an element of AB. So there you go. That's Rolle's theorem. So it follows essentially fairly quickly from the extreme value theorem. Now, that's all nice and good, but what we're really, we really tend to use more is the mean value theorem, which I'll state next. And the proof of the mean value theorem, it's very natural to prove the mean value theorem if you've just talked about Rolle's theorem, so we should do that. So the mean value theorem, it looks a lot like Rolle's theorem. So we abbreviate this guy MVT going forward, mean value theorem. Suppose f is a function such that, number one, f continuous on the closed interval from A to B. Number two, f differentiable on the open interval from A to B. And wait a minute. Oh, there's number three. And then there exists C in the open interval from A to B such that f prime of C is equal to f of B minus f of A divided by B minus A. And I'll just say it again. That is, there exists C in AB such that f of B minus f of A is equal to f prime of C times B minus A. Now, the graphical proof of this, quote-unquote proof, right? It's not really a proof, but a picture arguing its plausibility. It's pretty apparent once you just think about what you got, you know. So you've got, let's say f of a, let's say this is f of b, right? And I don't know what the function looks like. It could be that, for example. So what is f of b minus f of a over b minus a? That is the slope of the secant line for the function, which connects the point a comma f of a to b comma f of b. So this guy is the slope. It's this change in x over this change in y. Right?
Okay, so these reminds me of when we had to find the slope of a curve, you have to do x, changing x on changing y. Is it that way?
I mean, the slope, some people would define the slope of the tangent line to be the limit as delta x goes to 0 of delta y over delta x. We don't tend to use that notation much in mathematics because it's a little bit ambiguous, but you could look at the slope of the tangent line as being the secant line such that the delta x goes to 0. But in this context, the question is, at which point, you know? What does this theorem say, though? It says that the average rate of change of the function from b to a, which is what I've drawn in orange at the moment, it says it has to match the instantaneous rate of change of the function, the slope of the tangent line, at least some point in between, right? So if you start thinking about that geometrically, where are points on the function where you have the same slope? Well, there's a bunch of them in there, like here-ish, right? Like that point right there. There's like another one in here somewhere, right? There's another one up here. So these are all places where you'd have potential C for the theorem. Now, if you want a physical application of the mean value theorem, you could say, for example, I'm going to drive back home from school today. I live in Tuscaloosa. It's about 60 miles from here. All right. So, and typically it takes me an hour, right? So what's my average rate of change? You know, distance over time. You know, 60 miles an hour, right? So that means that there's at least some point in my journey going from here to Tuscaloosa where I'm going 60 miles an hour. Right? Now, I think if the cop pulls me over when I'm doing 90 and I tell him, but sir, I'm going to make it home in an hour and I only live 60 miles from school, my speed was 60, he's not going to care. It's the instantaneous velocity he's going to give me the ticket over, isn't it? Yeah, so. But that's not going to happen, right? No. Trucks will be in the way. I won't be able to go 90. Let's see here. Anyway, no, I'm messing with you. So here's the proof. It's one of my favorite proofs. So what we do is we invent a function which we can apply Rolle's theorem to prove this, right? So notice the difference between mean value theorem and Rolle's theorem. Mean value theorem doesn't have 0.3. Rolle's theorem has f of a equals f of b, right? So if we could use your imagination, we can kind of use Rolle's theorem to prove the mean value theorem. Let's see how. In fact, you'll find this proof in pretty much every calculus book. But let's see here. I think what I want to do is let S of x equal to f of a plus f of b minus f of a over b minus a times x minus a. So that is the equation of the secant line. That is the equation of the orange line that I drew over here. It has slope, the average rate of change, and it's based at a comma f of a. Now, check this function out. Notice S is continuous on AB and differentiable on a comma b. Now, do you believe me that it's differentiable? Do you believe me it's continuous? Why are those reasonable claims? So, how is f constructed? Oh, stink. Did I do it wrong? Oh, I feel like well, just a second here. I may be. No, I'm fine. I mean, it's silly. This is a line, right? I mean, f of b, f of a, these are given numbers. This is the equation of a line. Is that continuous and differentiable? I think so, yes. So, observe, what is S of a equal to? What happens when we put a here? We get a minus a, which is 0. So S of a is equal to f of a. What about S of b? See, the b minus a cancels. And then this cancels with that. And you get f of b, right? Hey. Oh! All right, this is good. This is fine. I'm just like, this doesn't get me the theorem I need. All right, so great. So we need to construct yet something else. Let h of x equal to s of x minus f of x. Actually, well, it's fine. How about this function? Well, is this function continuous? I mean, I will just say this function is both continuous and differentiable in the open interval because we're assuming that f is likewise and s is a line. And what is h of a? H of a is s of a minus f of a. H of b is s of b minus f of b. What are those equal to? Well, remember s of a was f of a, and s of b was f of b. So these are both 0. So now we have a function that is continuous, differentiable, and has matching values at the endpoints. So we may apply Rolle's theorem to h. Rolle's theorem for h of x yields that there exists a c in a to b such that what? H prime of c is equal to 0, right? But h prime of x is equal to f prime of x, well, excuse me, it's equal to s prime of x minus f prime of x, right? And what happens, what is the derivative of s prime of x? You can calculate it. The derivative is the slope. It's a line. The slope is f of b minus f of a over b minus a. So what does h prime of c equal to 0 tell us? So h prime of c equals to 0 tells us that f of b minus f of a over b minus a minus f prime of c equals to 0, right? But that implies exactly what the mean value theorem says, namely that f prime of c is equal to f of b minus f of a over b minus a. So this is the mean value theorem. Now, what does this tell us, though? What does the mean value theorem tell us about graphing a function? So let's think about it. Sorry we're going a little bit long today. We're still, I think today we'll be caught up because of remember the Monday we missed. I mean, related rates was supposed to be done Wednesday, but we kind of bled over today, you know. I think after today we're caught up, though. So discussion. Suppose f prime of x is greater than 0 for, x in some interval, let's say a to b. Well, let's say c to d. I don't know. You give me two letters you want. Whatever. C1 to C2? Sure. Okay. Let a comma b be a subset of C1, C2. Then what does the mean value theorem tell us? There exists, C in A to B, such that what? F prime of C equals to what? F of B minus F of A, divided by B minus A. But what did I assume here? At the moment, I've assumed that f prime of c is greater than 0, right? F prime of x is greater than 0 for all x in that. So if it's true for all x in C1 to C2, it's certainly true for f of c, f prime of c, right? So this is greater than 0. So what does that tell me? B minus a is what? By assumption here, a is less than b, right? So this is a positive quantity. So this tells me then that f of b minus f of a is greater than 0. Or in other words, f of a is less than f of b. Right? But a comma b was arbitrary. So this gives f increasing on C1 to C2. So, yes, increasing. I was about to say, couldn't it be, and in fact, it can't be constant either, can it? Right? If the derivative is positive on the interval, it implies that the function is, in fact, not just increasing, but strictly increasing. If the function is constant, it's technically increasing. It's kind of an annoying case, but true. All right? So this is really nice. If the derivative is positive, then the function's increasing. Now, when I say that, I'm talking about an interval of numbers, right? We actually can't talk about increasing and decreasing at just one point, technically. Like when we talk about increasing and decreasing for a function, it's always with respect to a set of points. But sometimes people abuse this result to say that if the derivative is positive, it's increasing at that point. That only makes sense if you're talking about a neighborhood of the point, technically. And then it's reasonable, because if the derivative is positive on a neighborhood of the point, that means that the function is increasing in that neighborhood. What would the same argument, right? The same exact argument. If you replace the condition f with f prime of x less than 0 on C1 to C2, then what? You get the same song and dance, but we get f prime of C equal to f of b minus f of a over b minus a less than 0, right? Which implies that f of b minus f of a is less than 0, which implies that f of a greater than f of b for all a and b, a less than b in the interval C1 to C2. So this would tell us that f is decreasing. On, C1 to C2. So this is very nice. This means if we want to figure out where the function's decreasing or where the function's increasing, all we have to do is look at the derivative of the function and determine where is it positive and where is it negative. And the first derivative test says a little bit more. What does the first derivative test say? Well, so I'm going to give you an example, and then I'll state the first derivative test on the basis of the example. Okay? Let's look. So we'll end with the first derivative test today, guys. But let's let f of x equal to x squared plus 2, rather x squared minus 9 times e to the x. We'll look at that. Let's try to find where this function's increasing and where it's decreasing. So df dx, what's that? So here's the problem. We're trying to find intervals of increase and decrease. That's the problem. All right, so what's df dx? We've got to do what? Product rule. So we've got d dx of x squared minus 9 times e to the x times the derivative of e to the x, right? So that's what? 2x e to the x plus x squared minus 9 e to the x. So what we got is we've got x squared plus 2x minus 9 times e to the x. Fermat's theorem says, like, local max and mins are going to happen where the derivative is 0. But here, just to take a step back here, remember we learned earlier that if the function's continuous, then it can only change from positive to negative where it's 0, right? So these critical numbers are going to be places where the derivative can change from positive to negative, right? The derivative function. So we're looking for where the derivative function is equal to 0. How can this be equal to 0? It's where the quadratic is 0, right? Because e to the x is non-zero. So we're just looking where x squared plus 2x minus 9 is equal to 0. So that's x plus 1 squared minus 10, which is, you know, this gives me solutions x equals to minus 1 plus or minus the square root of 10. You could use the quadratic formula on that. I mean, it's not particularly pretty, but those are the critical numbers. All right? And so I can draw a number line. And I'll put df dx here because we're talking about the derivative. And I'll put down the critical numbers, like minus 1 minus the square root of 10 here. And minus 1 plus the square root of 10 over here. The square root of 10 is about what? I don't know. 3.3 something, whatever. Right? What was the square root of 10?
It's 2.1.
Well, I'm really off. 2 point what?
2.16.
2.16? Oh, right, yeah. Wait. But 3 squared is 9. Square root of 10 should be larger than 3. Oh, you were giving me the whole number. You were giving me square root of 10 minus, you were giving me square root of 10 minus 1. I was asking for a square root of 10. You're fine. So you did this, and that is indeed 2.16, roughly speaking, right? Very good. And this is minus 4.16. Okay? And then, is the derivative continuous? Yes. So the intermediate value theorem says we can determine where it's plus and where it's minus by checking a point in each interval, right? So if you think about this quadratic, what's the graph of the quadratic look like? One of these deals, right? So it's positive on the ends and it's negative in the middle, which means that likewise this is going to be pluses, minus, right? So f increases on minus infinity to minus 1 minus root 10, and also on minus 1 plus root 10 to infinity. And f decreases between minus 1 minus root 10 and minus 1 plus root 10. Let's graph it. That is ultimately what we're after here, is learning how to use calculus to better inform our graphing. And then also we'll look at applications where we use calculus to maximize or minimize a function. Okay, so here, what's the limit as x goes to plus or minus infinity? I mean, x squared minus 9, think about it, as x goes to infinity, x squared minus 9 gets huge, exponential gets huge. This is going to infinity in both directions. The x-intercepts of this function are plus or minus 3. When you plug in 3, f of 3, f of minus 3 are 0. So f of 0 is minus 9. That's not calculus, that's just pre-calculus stuff. Those are points on the graph. This function is what? It is increasing on, let's see, in minus 1, it says minus, so minus 4.6 is like over here. And 2.16 is like over here. And so we said it was what? It was increasing. How? Oh, I was wrong. It doesn't go to sad. What happens to the exponential as x goes to minus infinity? That goes to 0, right? We'll learn something in about a week and a half that will allow us to argue that the exponential beats the x squared. It actually, this function limits to 0 as you go to minus infinity. That may not be clear, but you can kind of see, I mean, here's how I can see it. The function's increasing, right? Did I say increasing? Increasing. Is it decreasing? Where was I? Decreasing from minus 4.16 to 2.16. Decreasing. So whatever it is, I don't know, what is f of minus 4.16? Let me not try to guess. It's here somewhere. All right, this is totally schematic, but well, wait a minute. Is it positive or negative there? At minus 4.16, that's like about 16. That's 9, right? It's positive at minus 4.16. So I got to put my point on the right side of the graph, otherwise I'm going to get confused. So the function's up here at minus 4.16, right? It's pretty close to 0 because that e to the minus 4 power is super tiny. Okay? And then it's, what did I say? It's increasing. It was increasing up to that point. So what that means is that, and so like, this is a rather kind of indirect argument. We're going to find a better one later, but notice that the function only has y and x intercepts at minus 3 and 3, right? It's increasing from minus infinity to this point. That forces me to say that it has to do something like this. Because it's increasing, it doesn't cross the x-axis. It must be that it has a horizontal asymptote to 0 or to some other finite quantity. I can't really logically conclude it goes to 0, but I do know it can't cross 0 because the only zeros are this, right? X minus 3, x plus 3, e to the x. That's never 0, so minus 3, 3, the only choices. So that increasing, right? And it's also increasing from where? From here. So plug in 2, you've got like 4 minus 9. It's negative at 2. It's somewhere in here, right? And it's increasing past that point, right? And so there's no other x-intercepts except for, oh, look, but it does, wait a minute. Oh, but it goes through 3. Through 3 at 0. And then actually by common sense, we can see that the limit as x goes to infinity here is infinity. So it just keeps going and going and going. Right? Between this and that, it decreases, right? So it decreases. And, oh, and I know it goes, I mean, I know pre-calculus tells me it goes through x-axis there, right? I didn't do it quite right. I mean, if I did it right, it would be more like, goodness gracious. Well, it goes down there too. But it goes a little bit further down. I can't do it. I can't do it. The place where it's, this point right there should be the minus 2, the 2.16 should be the bottom. That's where the derivative is 0. Now, it's not, I haven't made the greatest graph, but you can see how calculus has allowed us to give a pretty accurate description of what this function looks like by knowing where it increases, where it decreases, where it has turning points. The turning points we could not have found without calculus. That's where the derivative was 0. Algebra does not reveal that. And next class, we'll talk about second derivatives. Second derivatives will tell us where it's concave down and concave up. That will give a further nuance to our graph. First derivative test, though, is what I'm going to stop with today here. What's the first derivative test say? It says, if f of c is a critical value, f of c being a critical value means that c is a critical number. then one, if f prime of c changes from minus to plus to if f prime of c, f prime of x rather, changes. That wind really sounds, if it was nighttime it'd be scary, from plus to minus, then f of c is, so we're getting blank 3, if f prime of x does not change sign, then f of c neither local max or min. So what I'm trying to get at here is, look at this, see what happened for our example? Oh, well, that table's there. So, ow. I'm fine. So when it changes from plus, when you're going up on the left side, but you're going down on the right side, it is a maximum. So it changes from plus to minus, local max. Other way around, local min. And that's the first derivative test. And if the derivative doesn't change sign, then it's neither a local max nor a local min. Can you guys think of an example where we have example 3? I'll stop with that today. The standard example I think of. Oh, straight line. Oh, well, that's, I mean, fair enough. I mean, f of x does not, f prime of x does not change sign. You know, to be clear, I should probably say f prime of x. Well, I am assuming f is not. Let me say from suppose f is not constant. Just to keep it quick here, because if f is constant, then every point in the domain is both a minimum and a maximum, and every point is a critical number. Like constants break everything, in some sense. But here's an interesting example: f of x equals to x cubed. F prime of x is 3x squared. That's equal to 0 only when x is equal to 0. Right? So there is the kind of point that case 3 concerns. See, the derivative, the number line for the derivative looks like this. It's got a critical number at 0. But the thing is, the cube function is always increasing. So here, 0 is a critical number, but it's neither a local max nor a local min. Yeah. But anyway, so that's it for today. Again, I'm sorry to keep you guys almost the whole time. Yeah, but we're now caught up. Woohoo!